I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to see a very important derivation that is regarding carrier concentration in extrinsic semiconductors P type. So we have discussed a few topics in this module, Introduction to Solids and Semiconductors. And in my previous class, I have discussed about the carrier concentration in N type. And today we are going to see the carrier concentration in P type semiconductors. So we are going to focus mainly on carrier concentration in P type semiconductors. Now the brief outline of how we are going to discuss this topic. First, we will try to understand what are extrinsic semiconductors. Then, in extrinsic semiconductors, we have two types, and we are now going to discuss about P type semiconductor. And then we'll derive an expression for the Fermi level. And from this derivation, we are going to deduce the expression for carrier concentration, that is P extrinsic, carrier concentration in P type extrinsic semiconductor. Now let us see the broad classification. In semiconductors, we have intrinsic semiconductor and extrinsic semiconductor. Intrinsic semiconductors are pure semiconductors. Pure means if we are taking a silicon crystal, all the atoms in the crystal are silicon atoms. There are no other atoms present. Then you say the crystal is in its pure form. So we call it as an intrinsic semiconductor. We have seen the examples here. Germanium and silicon are two good semiconductors. They are intrinsic semiconductors. Now coming to extrinsic semiconductors. Extrinsic semiconductors are impure semiconductors. Impure in the sense, if we are adding an atom belonging to some other element other than the semiconductor we have taken, then it becomes impure. So here again there is a classification into N type and P type. So in N type, we add a pentavalent impurity. If we are adding a pentavalent impurity means atoms that belong to the elements of the fifth group, pentavalent. Penta means 5. So which have 5 valence electrons. So when we are adding an impurity that has 5 valence electrons, then we call it as a pentavalent impurity. Examples we have from the fifth group, phosphorus, arsenic, antimony, etc. And we call them as donor impurities. Why we call them as donor impurity is, they have 5 valence electrons. We are adding this to a semiconductor, a pure semiconductor, which has 4 valence electrons. So there are 5 plus 4, total 9 electrons. So to attain stable configuration, it needs 8 electrons. So 1 electron is always extra and that is available to donate. So it acts as a donor impurity. So we are calling in this N type, whatever impurities we are adding, they are donor impurities and their concentration is denoted by Nd. Nd here denotes donor. Okay. And in donor impurity, always the number of electrons, Ne, is more than the number of holes. It means that electrons are the majority carriers. Electrons are majority carriers. So this is all about N type, and we have derived expression for the concentration, carrier concentration in N type. Today we are focusing on P type. So P type, we add a trivalent impurity. Trivalent means trivalent impurity has 3 valence electrons. It has 3 valence electrons. And what are the examples? Gallium, boron, indium, aluminium. All these are examples for trivalent impurities. They all belong to the third group. Now we call this as acceptor impurity. This is acceptor impurity and is denoted by Na. Why it is an acceptor impurity? Trivalent means 3 valence electron. It is added to a semiconductor which has 4 valence electrons. So 3 plus 4 is 7. It is always ready to accept 1 electron. So we are calling it as an acceptor impurity and its concentration is denoted by Na. And in this case, NH is greater than Ne, means the concentration of holes is more than the concentration of electrons. So the majority carriers here are holes. Holes are the majority carriers. This is what we need to understand before we go ahead. Okay. Now we will try to understand the difference between intrinsic and extrinsic semiconductor so that it is easy for us to make assumptions and derive. So intrinsic is in pure form, but extrinsic is impure. It is formed by adding either a trivalent or a pentavalent impurity. So trivalent impurity gives us P type and pentavalent impurity gives us N type. And in intrinsic semiconductors, holes and electrons are equal. So Ne is equal to NH. But in extrinsic semiconductor, the number of free holes are more in P type. So if we are talking about P type, NH is greater than Ne. And if we are talking about N type, Ne is greater than NH. All these differences we need to understand for doing the derivation. Then here, Fermi level lies in between the valence band and conduction band. So Fermi level here represents the highest occupied energy level, and since the number of electrons is equal to the number of holes, the Fermi level always lies in between the valence band and the conduction band. But whereas in case of extrinsic semiconductor, it varies. In P type, it lies near the valence band. And in N type, it lies near the conduction band. Then in the ratio of majority to minority carriers, actually here there is no majority and minority because both are equal. If we take the ratio because they are equal, Ne upon NH always should give us 1. That is unity. But in this case, in extrinsic semiconductor, the ratio of majority and minority carriers is not unity. If we are taking for P type, the majority carriers are holes, minority are electrons, so it will be greater than 1. Now let us see the extrinsic P type semiconductor, how it is formed. When a trivalent impurity like boron or aluminium or gallium, means all these elements belong to the third group and they have 3 valence electrons. They are trivalent impurities. They are added to a pure silicon or germanium. Silicon and germanium are 2 good semiconductors. So we are adding a trivalent impurity to a pure semiconductor. Then what happens? Each impurity atom forms 3 covalent bonds with 3 of its neighboring silicon atoms. So actually if you take a pure semiconductor, for example silicon, it consists of all silicon atoms arranged in a systematic fashion. We call it as a crystal lattice. They are arranged in a periodic fashion. Now when we are adding an impurity like boron, this boron replaces one of the atoms of silicon. Then what happens if you see in this figure here, if we are adding a boron impurity, so this replaces one silicon atom. We have one more silicon here. So this boron is surrounded by 4 silicon atoms. There are many silicon atoms. For example, we are taking a simple structure where one boron is surrounded by 4 silicon atoms. We have a number of silicon atoms here. For example, to understand how holes are formed, we have taken only one boron atom and 4 silicon atoms. Now, this boron atom, it has 3 valence electrons, 1, 2 and 3. 3 valence electrons, and these are the electrons that belong to silicon. Silicon will have 4 valence electrons, of course, like this. They have 4 valence electrons. Now this boron, because it has 3 valence electrons, it can form bonds with 3 of the neighboring atoms, 1, 2 and 3. Here it does not have an electron. So a deficiency of an electron, we call it as a hole. So there cannot be a bond formed here because it does not have an electron to form bond with silicon. So what we are seeing here is each of the impurity atom forms 3 covalent bonds with 3 of its neighboring atoms. There are 4 silicon atoms neighboring, but only with 3 it can form the bond because it has only 3 valence electrons, and therefore there is one deficiency of electron to form the 4th covalent bond. So it cannot attain the closed shell configuration. Now, how do we see the energy levels? Energy levels are created to the electron deficiencies just above the top of the valence band. So we need to understand this energy band diagram. This is called energy band diagram. So here, whatever I am showing here in the valence band, these are the range of energies possessed by valence electrons. And whatever we see here, conduction band, these are the range of energies possessed by conduction electrons or free electrons. Now, at T is equal to 0 Kelvin, the valence band is completely full and the conduction band is empty. And then because of doping here means addition of an impurity. So we have added an impurity, that is a trivalent impurity, and because of the trivalent impurity there are holes that are formed because there is a deficiency of electron, and the energies corresponding to these holes are denoted by EA. EA here represents the acceptor level. This is called the acceptor level because we have, depends upon the number of impurity atoms we add, we have the holes that are formed, and the holes, they are placed in this acceptor level because they are ready to accept one electron because they are deficiency of electrons. So these levels, the energies corresponding to them, we are denoting by acceptor level. So there is a level that is formed which we call it as the acceptor level, which consists of the holes that are formed due to the impurity that is added. Now how do we see this? In the silicon atom, whatever holes that are formed, as you add more and more boron atoms to the pure semiconductor, you have these holes, and these holes are represented in the acceptor level like this. So you have a valence band, there is a conduction band, and at T is equal to 0 Kelvin we are talking about because as the temperature varies, so these acceptors may get filled by the electrons from the valence band. So that we are going to see later. But at T is equal to 0 Kelvin, this is the scenario. The valence band is full, the conduction band is empty, and there is an acceptor level that lies just above the valence band. Now at around room temperature means from 0 Kelvin, we are just going above, say at 300 Kelvin, means at room temperature. many electrons that are nearer to the top of the valence band jump to the acceptor level. So when the temperature increases, some of the electrons in the valence band become free. They gain energy, they are free. So once they are free, they jump into the acceptor level because the acceptor level lies just above the valence band. Even a slight increase in energy will free the electrons and they jump into the acceptor level. And then only a few electrons jump to the conduction band. If you keep on adding more and more energy, then more electrons go. But at lower temperature, there are very few electrons that go into the conduction band. So when these electrons are shifting into the acceptor level and a very few of them shifting into the conduction band, correspondingly, there are holes that are generated in the valence band. So they leave behind holes in the valence band. So what we see here is the majority carriers are holes because there are very few electrons in the conduction band, but there are more holes in the valence band because some of them have shifted to the acceptor level and a very few have shifted to the conduction band. So what we have here is the majority carriers are holes in the valence band and the minority carriers are electrons that are there in the conduction band. Means what we see here is there are excess of holes. And a semiconductor which is formed by adding a trivalent impurity, we call it as P type semiconductor, and the impurities we call them as acceptor impurities. So this is the gist of what we have seen till now. Because of adding a trivalent impurity, there are excess holes that are formed. And we are calling it as a P type semiconductor and the impurity is a acceptor impurity because it is ready to accept the electrons. Now we are going to derive an expression for this carrier concentration, means the concentration of holes in the valence band, that is the majority carriers. But before doing the derivation, let us understand what carrier concentration is. We will understand the terms first and then we will derive the expression. So charge carrier density, it is also known as carrier concentration. It denotes the number of charge carriers per unit volume. This is what we need to understand. In other words, carrier concentration is also known as charge carrier density because in numericals when they are giving you the data, they may mention it as carrier concentration or charge carrier density. So it is very important for you to understand both mean the same. So what is charge carrier density? It is the number of charge carriers per unit volume. And what is its unit? Its SI unit is per meter cube, m power minus 3 or per meter cube. Suppose here in P type, I am calculating the concentration of holes. So it is so many number of holes per meter cube. So this is the SI unit for carrier concentration. And carrier concentration is a single number. It's a number and it represents the average carrier density over the whole material. Means whenever we are talking, we are just not talking about few atoms. It is the charges that are formed due to the entire material. So it is the average carrier density over the whole material. And how you are going to get it is obtained theoretically by integrating the density of states over the energy range of the charge carriers in the material. Means if you have to get the charge carrier density, what we need to do? We need to integrate. Integration is nothing but continuous summation. What we are going to add is we are going to add or we are going to take the density of states over the energy range of charge carriers in the material. Here we are talking about holes which lie in the valence band. So we will be integrating the energies in the entire valence band. That is the meaning of doing it theoretically. Now, in a pure semiconductor, the electron concentration in the conduction band and the hole concentration in the valence band are usually very small compared to the number of energy states. Means if you are taking a pure semiconductor and not adding any impurity to it, the concentration of the carriers, that is electrons in the conduction band and holes in the valence band, is very small when you compare to the density of states. But these concentrations can be changed by doping. The concentration of the charge carriers can be changed by doping. Doping here means what? Adding an impurity, addition of impurity. So we have already discussed about this point. By adding a trivalent impurity, we are getting P type and it is ready to accept the electrons. So it is accept the electrons by creating the holes. And when we are adding a pentavalent impurity, which can donate electrons to the conduction band, and the impurities are donor impurities. So we have two types of impurities here. One is a donor impurity, that is pentavalent impurity, and the other is an acceptor impurity, which is a trivalent impurity. So by adding this, what we are doing, we are increasing the concentration of carriers. So both donors and acceptors are referred to as dopants. So when we are talking about the impurities, we are calling them as dopants. Whether it is an acceptor impurity or a donor impurity, it is called as dopant. Now at room temperature, what happens? Each donor in N-type semiconductor supplies one electron to the conduction band. Means as you increase the temperature, suppose one bond is broken. So one electron will come to the donor level. And the electron concentration in the conduction band is approximately equal to the donor concentration. So more the number of atoms, donor atoms we add, more the number of electrons in the conduction band. Now in a similar way, this is for N-type. In a similar way, at room temperature, what happens in P-type? Each acceptor creates one hole in the valence band and the hole concentration P in the valence band is equal to the acceptor concentration. So it all depends upon the concentration of the atoms we are adding, whether it is the donor atoms or the acceptor atoms. In P-type, it is the acceptor atoms, because of which there is increase in the concentration of holes. So at low temperatures, the hole concentration P in the valence band is equal to the acceptor concentration Na. So our entire derivation is going to base on this. Hope you understand why we are talking in terms of acceptor concentration. Because of adding acceptor impurities, we are getting holes in the valence band and we are trying to calculate the carrier concentration of these holes in the valence band. Now to do this derivation, first what we have to know is the acceptor concentration. So what is acceptor concentration? Let Na be the acceptor concentration. That is the number of acceptor atoms per unit volume we have added. So that becomes the acceptor concentration. Now the expression for the concentration of the acceptors is given by Na exponential minus of Ea minus Ef by kBt. So Na here represents what? Number of acceptor atoms per unit volume is Na. Ea here represents the acceptor level. Ea represents what? Acceptor level. Ef represents Fermi level. Ef is the Fermi level and Kb here denotes Boltzmann constant. Kb is the Boltzmann constant, whose value is given by 1.38 into 10 to the power of minus 23 joules per Kelvin. And T is the temperature. So what we are trying to see here is what is the concentration due to the acceptors that we have added. It is given by Na exponential minus of Ea minus Ef by kVt. We have defined all the terms. You can also write this exponential as e power. Both mean the same. So it can be written as Na e power Ef minus Ea by kVt. This is equation 1. So now we know the concentration of the donor atoms that we have added to a pure semiconductor. Now we have derived an expression for P, that is the concentration of holes in the valence band. We have already derived this expression. You can refer to our previous videos for this derivation, hole concentration in valence band. So what is the concentration of holes in the valence band given by 2 into 2 pi mh star kt, or this is the same as kBt, by h square exponential Ev minus Ef by kt. Here 2 pi are constants. mh star denotes the effective mass. It is the effective mass of hole. That is why we are putting the suffix h. mh star here is the effective mass of hole. So whenever a electron is in a periodic potential, we always talk in terms of effective mass. So mh, kb is the Boltzmann constant, T is the temperature, h again here is the Planck's constant. H is the Planck's constant. We have exponential Ev minus Ef by kT. Ef is the Fermi level we have seen. Ev here represents the topmost energy level in valence band. Top energy level in valence band. So this is about the hole concentration. Now what we have understood, at very low temperature, the number of holes in the valence band must be equal to the number of acceptor atoms per unit volume. This is what we have discussed. So because we are adding impurities, the holes are being generated in the valence band, and at low temperatures, the number of holes in the valence band must be equal to the number of acceptor atoms per unit volume. So we are going to equate these two equations. Whatever two equations we have written, one for the number of acceptor atoms per unit volume and then the number of holes in the valence band. These are the equations 1 and 2. We are going to equate them now. So 2 into 2 pi mp kBt by h square power 3 by 2 e power minus Ef plus Ev by kBt. This represents the P, that is the concentration of holes in the valence band. And here Na into e power Ef minus Ea by kBt represents the concentration of donor atoms. This is due to the donor atoms. Now we are going to simplify this equation. How we are going to do it is, we will take both the exponential terms onto one side and bring this term, the constants, onto the other side. So what we get here is e power minus Ef plus Ev by kBt, which is there here, and this term, this e power Ef minus Ea by kBt, it comes to the denominator. So what we have here is exponential minus Ef plus Ev by kBt, and in the denominator we have e power Ef minus Ea by kBt. We are just transposing the terms. Now this term comes onto the right hand side into the denominator. So we have Na here on the right hand side and this term comes to the denominator. So we are just trying to simplify this. Now what we are going to do is, we are going to take the logarithm. So before taking the logarithm, I'll try to simplify this and write. So what we have in the numerator here is e power minus Ef plus EV. And in the denominator, we have plus EF minus EA. So this plus EF, if it comes up, minus EF. And minus EA, if it comes up, plus EA upon KBT. I'm just only doing the left hand side, simplification of the left hand side. So what we have here, minus EF and minus EF. So e power minus 2 EF. We have 2 EFs in negative here. So we get minus 2 EF plus EV plus EA by KBT. So this is what our LHS is reducing to. E power minus 2F plus EV plus EA. You can write it like this also upon KBT. Now what we are going to do is we are going to take the logarithm on both the sides. So when we take the logarithm on both the sides, we know exponential of log x. Sorry, I'll write it the other way because we are taking the logarithm of exponential. So logarithm of exponential x is equal to x, simply x. So when we are taking log on both the sides, here we are getting a log and the right hand side term as it is we are writing. But on the left hand side, what we are using this formula, logarithm of exponential x gives us x. This is our x after simplifying. Minus 2EF plus EV plus EVA by KBT. This is equal to log of NA by 2 into 2 pi MP KBT by h square power 3 by 2. Now we want to find EF. So we are going to take KBT onto the other side. So we are just having the numerator minus 2EF plus EV plus EA is equal to, this KBT goes to the numerator. So we have KBT log NA upon the whole term we have. Now if I have to write for EF, what I do, we can take minus 2EF other side and bring KBT here, or multiply with minus on both the sides also is the same. So from this term, what we can write here is EV plus EA minus KBT log NA upon 2 into 2 pi MP KBT by h square power 3 by 2 should be equal to 2EF. So I made it simple. I've kept EV plus EA here only. I brought the KBT term onto this side and have taken 2EF onto the right hand side. So this also becomes plus, this also becomes plus. Now I want only EF. So EF will be equal to what? We have EV plus EA by 2 minus KBT by 2 log the whole term we have. So what we are having for EF now? EV plus EA by 2 minus KBT by 2 log the whole term we have. So that is what we are writing here. EF is equal to EV plus EA by 2 minus KBT by 2. Hope you understand why we are getting this minus. Because we want to find EF, we have taken EF onto the other side and KBT onto the left hand side. So we have logarithm of NA upon 2 into 2 pi MP KBT by h square power 3 by 2. This is at any temperature more than 0 Kelvin, above 0 Kelvin. So I can say this is a generalized expression for EF, general form of expression. Now if we put the conditions, first case at T is equal to 0 Kelvin. So at T is equal to 0 Kelvin, what will happen here? In this term, for T, if I substitute 0, then what happens? 0 into something is 0. So the whole term will go to 0. At T is equal to 0 Kelvin. On substituting for T, 0. So what we are left with is EF is equal to EV plus EA by 2. So we are going to simplify the expression and write it as at T is equal to 0 Kelvin, EF is equal to EV plus EA by 2. What does this represent? this represents that EF lies between EV and EA. This is a very important conclusion. Why? Because I told you Fermi level decides the conductivity in elements. So here, when we are talking about the Fermi level, this is the valence band, this is the conduction band, and now we have an acceptor level here, EA. This is the topmost EB, this is EC. Now, where is the Fermi level lying? It lies in between EV and EA. So, if I write this as EA, so the Fermi level lies in between EV and EA. I can write the Fermi level here. Means, in an intrinsic semiconductor, the Fermi level lies exactly in between the energy gap. But because of adding an impurity, P type, the Fermi level is shifting towards the valence band. So, it lies between EV and EA. And at any temperature more than 0 Kelvin, we have the general expression. Then what happens at any temperature? As the temperature increases, the Fermi level slightly drops towards the valence band. So, now this is at the center of EV and EA, we have seen lies in between. Now, if you keep on increasing the temperature, what happens? This Fermi level will shift towards the valence band. Now, in order to get the carrier concentration in P type, now we want to see the entire concentration, that is the number of charge carriers per unit volume. So, we have this expression 2 into 2 pi mp kBt by h square power 3 by 2 e power minus EF minus EV by kBt, or simply you can write it as e power minus EF plus EV, because we can take this minus also inside and write it as minus EF plus EV by kBt, any one of the expressions we take. And now whatever value we have got for EF. So what is the value we have got for EF now? EF is equal to EV plus EA by 2 plus kBt by 2 log Na upon 2 into 2 pi mp kBt by h square power 3 by 2. So, this is the term we got. We have derived now for EF. This is what we have got for EF. And only at 0 Kelvin we said EF is equal to EV plus EA by 2. Now, at any temperature you take, if you have to find the carrier concentration. So, what do we have to do? We have to substitute this value of EF in this expression. In this EF, we need to substitute this expression. So, N extrinsic P type will be given by 2 into 2 pi mp kBt by h square power 3 by 2. We are writing this term as it is. Then we have exponential. So, we are writing exponential. And in place of EF, we have to write this term. No? So, we have EV plus EA by 2. So, we are writing minus of EV plus EA by 2. And we also have kBt by 2 log Na by 2 into 2 pi mp kBt by h square. So, the same term we are writing. And then after that we have plus EV. So, we are writing plus EV. So, only thing what you have to understand is in place of EF, we are going to substitute this entire expression. So, now we are going to simplify this. So, for simplifying, we are going to do one things to formulae. A power m into A power n is equal to A power m plus n. Or here what we have is exponential of A plus B. We can write it as exponential of A into exponential of B. E power A into E power B we can write it as. And also when we are taking that, we have exponential of log x is equal to x. So these two formulae we are going to use here. Exponential of A plus B is equal to exponential of A into B, and exponential log x is equal to x. So when you are taking the exponential and logarithm on both the sides, 2 into 2 pi mp kBt by h square power 3 by 2. We have exponential EV minus EA by 2 kBt because we are writing it as we have exponential of A plus B. So this is the first term and this is the second term. Now we are writing exponential of the first term into exponential of log. So it becomes only x. So we are simply writing Na power half by 2 power half 2 pi mp kBt by h square power 3 by 4. Why we are getting this half here is we have kBt by 2 log Na by 2 into 2 pi mp kBt by h square power 3 by 2. This is what we have. Now for this we also have a denominator by kBt. So kBt will get cancelled. So whenever I have a log m, I can write it as log m power a. So what I can do here is I'll write logarithm of Na by 2 into 2 pi mp kBt by h square power 3 by 2 power half. So whatever 1 by 2 that is left here, we are taking it as a power here. Now when we are taking exponential of log, this term, the whole term I am writing it as x. So exponential of log gives us only x. So I am writing only the x term. And we are having the power half. This is due to this we have half. So now I'll write this power to the numerator also, Na power half, and in the denominator also 2 power half. And here we have 3 by 2 into 1 by 2 we have 3 by 4. So now we are writing an extrinsic. We are finding the concentration for a P type extrinsic semiconductor. So here whatever terms we have power half, we are now going to simplify. In the denominator we have 2 power half, in the numerator we have 2. So 2 upon 2 power half will be 2 power 1 minus half. This is simple mathematics. So we get 2 power half. So we are writing 2 power half. And again you have Na power half. So I can combine both and write 2 Na power half because 2 is also having power half and Na is also having power half. So 2 Na power half. And here we have 2 pi mp kBt by h square power 3 by 2. Here we have 2 pi mp kBt by h square power 3 by 4. So in the numerator I have x power 3 by 2. In the denominator I have x power 3 by 4. So how do we write this? X power 3 by 2 minus 3 by 4. So we will be left with x power 3 by 4. So that is why we are having this is x 2 pi mp kBt by h square power 3 by 4. And then this exponential term as it is, but we are taking a minus outside and writing it as Ea minus Ev by 2 kBt. It is the same as writing it as Ev minus Ea by 2 kBt. So the final expression we have for extrinsic semiconductor is 2 Na power half into 2 pi mp kBt by h square power 3 by 4 exponential minus of Ea minus Ev by 2 kBt. Okay. In similar lines, we have derived the expression for N type also. If you are following the N type, understanding the P type becomes very easy. So I hope you understood it. For more clarification regarding this derivation, you can refer to P.K. Palaniswamy, Engineering Physics, and also Engineering Physics by Gaur and Gupta, and also Modern Engineering Physics by Vijay Kumar and Chandralingam. Thank you. See you again in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.